A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. What if we could simulate a 50-atom molecule in minutes instead of years? That is not a scene from a science fiction movie anymore. It is the literal promise of quantum advantage in drug discovery, and we are seeing the first real benchmarks of it right now.
Herman Poppleberry here, and you are right, Corn. With IBM's 1121 qubit Condor processor out in the world, and Google's 2025 roadmap hitting its targets for error, corrected logical qubits, we are officially crossing that bridge from theoretical physics into practical industry benchmarks.
It is about time. I feel like we have been hearing about the quantum revolution for a decade, but it always felt like it was 10 years away, like nuclear fusion or a decent printer that actually works when you need it. But Daniel sent us a prompt today that really forces us to move past the vague hype. He wants 10 specific use cases where quantum computing delivers a measurable, quantifiable improvement over classical systems. No, maybe someday, fluff. Just the hard data on where this stuff actually works.
I love this prompt because it moves the goalposts. We are not talking about quantum everything. Quantum computers are actually worse than your laptop for most things, like checking email or watching videos. But there are these specific high-dimensional problem domains where the number of variables grows exponentially, and that is where classical hardware just hits a brick wall. By the way, today's episode is powered by Google Gemini 3 Flash, which is fitting since we are talking about the cutting edge of computation.
So Daniel sent us this one, and he is looking for 10 use cases. He says each one should describe a scenario where quantum brings a significant and measurable improvement over non-quantum computing. He is looking for the concretization of the tech. So, Herman, where do we even start with this? There is a lot to unpack, but I think we should establish what makes a problem quantum ready before we hit the list.
That is the perfect place to start. A problem is quantum ready if it involves strong correlations or exponential scaling. Think of a maze. A classical computer is like a mouse running through the maze, hitting a wall, turning around, and trying again. It is fast, but it is linear. A quantum computer is more like a mist that enters the maze and occupies every path simultaneously. It finds the exit because it is everywhere at once through superposition.
I promised no analogies, Herman, but I will allow that one because it actually helps frame the measurable improvement metric. We are looking for time to solution, accuracy gains, or massive cost reductions. If a supercomputer takes a year and a quantum system takes an hour, that is the ballgame. Let's dive into the first big one, pharmaceutical drug discovery. This is the one everyone points to, but what is the actual mechanism there?
The mechanism is molecular simulation, specifically looking at protein-ligand binding. If you want to know how a new drug molecule interacts with a target protein in the body, you have to simulate electron interactions. In a classical computer, every time you add an electron to the simulation, the complexity doubles. It is a power law nightmare. Quantum computers, however, use qubits that operate on the same quantum mechanical rules as the electrons they are simulating. They are digital twins of the molecules.
But wait, why can't we just build a bigger supercomputer? If we just keep adding GPUs, don't we eventually solve the complexity?
You'd think so, but the math says no. To simulate a molecule with just 70 electrons exactly, you would need a classical computer the size of the Earth. By the time you get to a complex protein, you'd need a computer the size of the known universe. It's not a hardware limitation, it's a mathematical one. Quantum systems bypass this because one qubit can represent multiple states of an electron simultaneously.
And we have actual numbers on this now, right? I saw a report about a collaboration between Roche and Cambridge Quantum Computing.
We do. In 2024, they demonstrated a 100-fold speedup in molecular docking simulations for a 20-atom system using variational quantum eigensolvers, or VQE. Now, 100 times faster sounds great, but the real kicker is the hit rate. Right now, 90% of drug candidates fail in clinical trials because we cannot accurately predict toxicity or efficacy in the digital phase. If quantum simulation can bump that success rate by even 10%, you are saving billions of dollars and years of R&D time.
It is the difference between guessing and knowing. If you can simulate the chemistry perfectly, you do not have to fail in the lab as often. That leads us pretty naturally into the second use case, which is a bit different but shares that complexity problem: financial portfolio optimization. This is where the big banks are putting their money.
This is huge for the Monte Carlo simulations that hedge funds and banks run every night. They are trying to predict the risk of a portfolio under thousands of different market conditions. On classical hardware, to get a certain level of accuracy, you need Noller's number of samples. If you want to be twice as accurate, you need 4 times as many samples. But quantum algorithms, specifically quantum amplitude estimation, give you a quadratic speedup. You only need the square root of NR samples.
So if a simulation takes a supercomputer 24 hours to run, which is why banks usually do them overnight, a quantum system could do it in minutes.
Well, I should not say exactly, but that is the projected impact. Being able to do real-time risk adjustments during active trading hours instead of waiting for the overnight batch is a massive competitive advantage. It is the difference between reacting to a market crash while it is happening versus reading about why you lost money the next morning.
But how does that work in practice? Are banks actually plugging quantum chips into their trading desks?
Not yet. Right now, it's a hybrid approach. They use classical systems for the bulk of the data processing and then offload the specific high-dimensional probability calculations to a quantum processor. Goldman Sachs and JP Morgan are already testing these hybrid workflows. They've found that for certain derivative pricing models, the quantum approach reduces the error noise significantly compared to classical approximations.
I can see why Wall Street is obsessed. Let's pivot to something more physical. Use case number 3, logistics and routing. This is the classic traveling salesman problem, but on a global scale. Think UPS, FedEx, or the Suez Canal.
This is where D-Wave has been making a lot of noise with quantum annealing. In 2025, they ran a benchmark for logistics routing that reduced computation time from 48 hours to just 90 minutes for a 1,000-node network. When you are managing a fleet of thousands of delivery vehicles, the number of possible routes is higher than the number of atoms in the known universe. Classical computers use heuristics, which is basically a fancy word for a very good guess.
But good enough is not the same as optimal. If you can find the actual shortest path, you are saving millions of gallons of fuel.
And it is not just about the shortest path, it is about real-time rerouting. If a bridge closes or weather hits, a classical system might take hours to find a new good route. A quantum algorithm like the Quantum Approximate Optimization Algorithm, or QAOA, can explore that entire solution space simultaneously to find the new optimum in seconds. McKinsey estimated that this kind of quantum optimization could create $10 to $25 billion in value for the logistics sector through just a 2 to 5% annual efficiency gain.
5% does not sound like a lot until you realize it is 5% of the entire global supply chain. That is real money. Now, number 4 on our list is one I find fascinating because it is so specific: nitrogen fixation and fertilizer production. This sounds boring, but it is actually a global energy crisis hidden in plain sight.
It is one of the most important chemical reactions on Earth. The Haber-Bosch process, which we use to make ammonia for fertilizer, consumes 1 to 2% of the entire world's energy supply. It requires massive heat and pressure because we are basically trying to force nature to do something it does not want to do.
But plants do this for free, at room temperature.
They do. They use an enzyme called FeMoco. The problem is that FeMoco is so complex that we cannot simulate it on a classical computer to understand how it works. It is a strong correlation problem involving iron and molybdenum atoms. Quantum computers can act as the perfect digital twin for that enzyme. If we can use a quantum simulation to design a synthetic catalyst that mimics FemoCo, we could potentially reduce global energy consumption by 1%. That is a massive dent in the global carbon footprint just from one chemical simulation.
Is there a fun fact moment here? Because I feel like I read somewhere that we've been trying to solve this since the 1900s.
We have. The Haber-Bosch process was actually developed in 1909. We are still using 115-year-old technology to feed the world because the molecular biology of a single clover plant is more computationally complex than anything a classical supercomputer can handle. It's a humbling reminder of where we are.
It is wild that we have been using the same brute force method for 100 years because we just did not have the resolution to see how nature does it. Okay, that is the first four: drug discovery, finance, logistics, and fertilizer. They all share this theme of simulating reality, or optimizing complexity. But as we move into the second half of the list, things get a bit more intense. Specifically, use case number 5, cryptography. This is the one that keeps government spooks up at night.
This is the harvest now, decrypt later threat. State actors are capturing encrypted data today, even if they cannot read it, because they know that in 10 or 15 years, a quantum computer running Shor's algorithm will be able to crack RSA-248 encryption in seconds.
So, what is the measurable improvement here? Is it just, we can break your stuff faster?
It is the shift to quantum key distribution, or QKD. Unlike classical encryption, which is based on math problems that are just hard to solve, QKD is based on the laws of physics, specifically Heisenberg's uncertainty principle. If you try to measure a quantum state, you change it. So, if an eavesdropper tries to intercept a quantum key, the sender and receiver will immediately see the disturbance. It provides what we call information theoretic security. It is mathematically proven to be unbreakable, regardless of how much computing power the attacker has.
Wait, so if I try to peek at the data itself changes. How does the receiver know I looked?
Because they check a portion of the key. If the error rate is higher than a certain threshold, they know the quantum state was collapsed by an observer. They just throw the key away and start over. It's the only form of communication where the laws of the universe act as the security guard.
So we go from really hard to crack to physically impossible to crack without being noticed. That is a pretty significant upgrade.
It is the ultimate security blanket for sensitive data. Now, for number 6, let's talk about something that affects everyone, climate modeling. This is another area where the scale of the data just dwarfs classical supercomputers.
I thought we were already pretty good at weather. My phone tells me when it's going to rain within 10 minutes.
That's local weather, which is short-term fluid dynamics. Climate modeling is much harder because it involves turbulent flows, ocean-atmosphere feedback loops, and carbon cycles spanning decades. In 2025, IBM ran an experiment on climate modeling that showed a 50-fold reduction in simulation time for a 10-kilometer resolution atmospheric model. Current weather and climate models have to make trade-offs. You can have a high-resolution model of a small area or a low-resolution model of the whole planet. Quantum-enhanced fluid dynamics allows for both.
And that is not just about knowing if it will rain on your parade. It is about predicting extreme weather events, hurricane paths, and long-term drought cycles with enough lead time to actually do something about it.
And it ties into use case number 8, which I will jump to for a second. Carbon capture research. If we want to scrub CO2 from the atmosphere, we need new chemical adsorbents. Just like with the fertilizer catalyst, designing these materials requires precise modeling of gas-solid interactions at the quantum level. We are looking for a material that can grab CO2 molecules out of the air efficiently and cheaply. Classical computers just cannot see the handshake between the CO2 and the adsorbent clearly enough to optimize it. Quantum can.
So we are talking about making carbon capture economically viable for the first time. That is a game changer for the climate. Okay, back to the list. Number 7, artificial intelligence. I know, everyone is talking about AI, but how does quantum actually make it better?
It comes down to linear algebra. Training large language models or fraud detection systems is basically just doing billions of matrix multiplications. Quantum computers can perform certain linear algebra operations exponentially faster than classical GPUs for specific high-dimensional data structures.
Is this why we keep hearing about quantum neural networks?
A classical neural network uses bits to represent weights. A quantum neural network uses qubits. This allows the model to explore a much larger feature space. For example, in fraud detection, a classical system might look at 50 variables to spot a stolen credit card. A quantum system could look at 5,000 variables simultaneously and find correlations between them that are invisible to classical logic. It's like going from a 2D map to a 3D hologram of the data.
So we are talking about faster training times?
Faster training, yes, but also a significant reduction in energy consumption. Training a top-tier LLM today uses as much electricity as a small town. Quantum-enhanced machine learning could potentially do that for a fraction of the power. Also, it allows for quantum-enhanced gradient descent, which helps neural networks find the optimal state faster without getting stuck in local minima.
I love the idea of AI that is not just smarter, but also less of a power hog. Let's move to number 9, material science, specifically superconductivity. This is the holy grail of energy.
If we could find a material that exhibits superconductivity at room temperature, we would eliminate the 5 to 10% energy loss we currently experience in the global power grid. Right now, we lose a massive amount of electricity just moving it from the power plant to your house because of resistance in the wires.
And the reason we have not found a room temperature superconductor yet is that we cannot simulate them, right?
Correct. High-temperature superconductors involve strongly correlated electrons. In a classical computer, you can simulate a few atoms, but once you get to a meaningful chunk of material, the math explodes. Quantum computers are built from the same quantum mechanical rules as these materials. They are the perfect environment to hunt for the right atomic structure that allows electrons to flow without resistance at room temperature.
Is there a specific material we're looking at, or is it just a blind search?
We're looking at cuprates and nickelates. These are complex ceramic-like materials. In 2024, researchers used a small-scale quantum simulator to model the Hubbard model, which is the mathematical framework for how these electrons behave. They found a specific magnetic alignment that suggests a path to higher temperature stability. We're basically using a quantum computer to write the recipe for a material that doesn't exist yet.
Imagine a world where your phone never gets hot and the power grid is 100% efficient. That is the measurable impact there. Finally, number 10, natural language processing, or NLP. But specifically, semantic mapping. This is different from the AI training we talked about.
This is about understanding meaning rather than just probability. Classical NLP, like the LLMs we use today, represents words as vectors in a high-dimensional space. It is very good at predicting the next word, but it does not really understand context in a deep way. Quantum Natural Language Processing, or QNLP, maps words to quantum states in a Hilbert space.
You are losing me with Hilbert space, Herman. Give it to me in plain English.
Human language is full of overlap, sarcasm, and ambiguity. A single word can mean 3 different things based on the subtle context of the sentence. Quantum states can represent those overlapping meanings through superposition much more naturally than classical vectors can. It allows a computer to represent the complex, nuanced meaning of a sentence as a single quantum state.
So we are talking about virtual assistants that actually get sarcasm, or real-time translation that does not lose the cultural nuance?
Well, there I go, saying it again. But yes, that is the goal. Dramatic improvements in translation accuracy and sentiment analysis for complex speech. Think of a legal contract where one word's meaning depends on 3 other clauses. A classical system reads those sequentially. A QNLP system sees the entire web of meaning at once.
That is an incredible list. Drug discovery, finance, logistics, fertilizer, crypto, climate, AI, carbon capture, superconductors, and language. It seems like the common thread is that we are finally getting the microscope. We need to see the world as it actually is, which is quantum, rather than trying to force it into the bits of a classical computer.
That is a great way to put it. We are moving from simulating a simulation to simulating reality.
So, looking at these 10, which one do you think hits quantum advantage first? Like, Where is the first moment where a CEO stands up and says, "We did this with a quantum computer because we literally could not do it any other way"?
I think it is a toss-up between logistics and drug discovery. D-Wave is already doing pilot programs in logistics that are hovering right on the edge of classical performance, but drug discovery is where the most value is. If a pharma giant can shave 2 years off a 10-year R&D cycle, that is worth billions. We are already seeing those 2024 and 2025 benchmarks from Roche and IBM. I think by 2027 or 2028, we will see the first drug entering clinical trials that was designed using a quantum-first approach.
But wait, how do we know the quantum computer isn't just hallucinating the result? Like how an AI can be confidently wrong.
That's where quantum verification comes in. For many of these problems, like optimization or factoring, it's very hard to find the answer, but very easy to verify it. If a quantum computer gives you the shortest route for 10,000 trucks, a classical computer can check that specific route in milliseconds to confirm it works. We use the quantum computer for the heavy lifting of the search, and the classical computer as the fact checker.
That is a wild thought. A literal quantum drug. But for the people listening who are not running a multi-billion-dollar pharma company, what should they be doing? If I am a tech lead or a developer, is this something I can actually touch today?
You do not need to build a dilution refrigerator in your basement. Most companies today are using Quantum as a Service, or KS. You can log into IBM Quantum, AWS, Break It, or Microsoft Azure Quantum and start running experiments on actual hardware or high-fidelity simulators today.
So the advice is, start benchmarking now. If you have an optimization problem or a chemistry problem, do not wait for the hardware to be perfect. Start writing the quantum-ready algorithms in libraries like Qiskit or Cirq today.
Precisely. There is a massive talent gap. There are not enough developers who know how to think in quantum. The math is different, the logic is different. If you wait until the hardware is fully mature to start learning, you are going to be 5 years behind the curve. It's not just about learning a new programming language, it's about learning a new way of reasoning about information.
It is like the early days of the internet. You did not need to know how to build a router to start building a website. You just needed to understand the protocol.
And the protocol here is linear algebra and probability. If you can master that, you can bridge the gap.
Another thing that struck me from Daniel's notes was the energy advantage. We always talk about speed, but the power consumption of these massive AI clusters is becoming a real political and economic issue. If quantum can do the same work for 10% of the energy, that might be the advantage. That drives adoption faster than pure speed.
I think you are right. Photonic quantum computers, like the ones from Quandela, can operate at room temperature for certain tasks and use a fraction of the electricity of a classical supercomputer. In a world where energy prices are volatile and carbon taxes are becoming a reality, the green argument for quantum is very compelling.
It is the efficient computer, not just the fast one. Now we should address the sovereignty race that Daniel mentioned. This is the geopolitical side of it. Why are countries like Canada, Israel, and China investing billions into domestic quantum hardware? Why not just use IBM's cloud?
It is all about that harvest now, decrypt later threat we talked about. If you rely on a foreign power's quantum cloud for your most sensitive simulations or encryption keys, you have a massive security hole. If a country can achieve quantum sovereignty, they can protect their own data while potentially gaining an eye into everyone else's. It is the new space race, but instead of the moon, we are racing for the subatomic high ground.
It feels like a very high-stakes game of poker, where one player is slowly getting X-ray glasses.
That is a very Korn-esque way of putting it. But it is accurate. And the stakes aren't just military, they're economic. The first country to master quantum simulated materials will own the patents for the next generation of batteries, solar cells, and semiconductors.
So, we have covered the what and the why. Let's talk about the when. We are in 2026. Google says error-corrected logical qubits by 2029. IBM says 10,000 plus qubits by 2030. Is that the timeline for these 10 use cases to go from pilots to the standard way we do business?
I think the 2030 window is when the convergence happens. Right now, these 10 use cases are being explored in silos. But imagine when you can combine quantum-enhanced drug discovery with quantum-enhanced climate modeling to design a new medicine that is also carbon neutral to produce. Or using quantum AI to optimize the supply chain for a room temperature superconductor you just discovered using a quantum simulation.
That is when the world starts looking very different, very quickly. It is an acceleration of acceleration.
It is. And the most exciting part is the stuff we haven't even thought of yet. Every time humanity gets a new tool for calculation, from the abacus to the slide rule to the silicon chip, we end up solving problems we didn't even know were problems. We're currently at the vacuum tube stage of quantum. Imagine where we'll be at the smartphone stage.
I am just waiting for the quantum-enhanced coffee maker that knows exactly when I need a caffeine hit before I even realize I am tired.
We might be a few years away from that one, Korn. But hey, if it can solve the traveling salesman problem for your morning commute, that's a start.
A sloth can dream, Ermin. A sloth can dream. This has been a fascinating deep dive. I think it is important to remember that while the hype can be exhausting, the underlying physics is solid. We are not talking about magic. We are talking about a more fundamental way of processing information.
Well said. It is the transition from calculating to simulating. If the 20th century was the century of the atom, the 21st is the century of the qubit.
Before we wrap up, let's hit the main takeaways for everyone listening. Number 1, quantum is not for everything, but for high-dimensional problems in chemistry, finance, and logistics, it is already showing measurable gains. Number 2, the energy advantage might be just as important as the speed advantage. And number 3, if you are in a technical field, start playing with kiosks today. The hardware is coming, but the talent gap is the real bottleneck.
And keep an eye on those benchmarks. Don't look at qubit counts as much as you look at time to solution for specific industrial problems. That is the real metric that matters. If a company claims they have 5,000 qubits but can't solve a simple optimization faster than a MacBook, it doesn't matter.
This was a great prompt from Daniel. It really forced us to get concrete. I feel like I actually understand why we are spending billions on these giant white thermoses in the basement of research labs.
They are the most sophisticated tools we have ever built. It is an exciting time to be a nerd.
It is an exciting time to be a brother of a nerd, too. I get to hear all about it. Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes.
And a big thanks to Modal for providing the GPU credits that power this show's generation pipeline. We couldn't do it without that serverless horsepower.
This has been My Weird Prompts. If you're enjoying the show, a quick review on your podcast app really helps us reach new listeners who are curious about this weird world we are building.
Find us at myweirdprompts.com for the RSS feed and all the ways to subscribe. We will be back next time with another prompt from Daniel.
Keep it weird, everyone.
See ya.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the flows from sloth.